Hello, everybody. We're going to be doing our topic 4 lesson today. This is a fairly lengthy one, so that's one of the reasons why I wanted to make this a YouTube video. There's actually a lot of little mini things we're going to talk about. Ultimately, I've called this radioactive decay, but really what we're going to talk about today is the events and the discoveries that led up to our next topic, which is nuclear physics. And on the timeline that I hopefully have written on the board somewhere, our timeline usually, I end my timeline in the 1940s with the explosion of the first nuclear bomb in Japan in 1945, the end of the World War. And that's what we're really getting to now is the nuclear physics and discovering the fundamental forces that at a subatomic level, how we're able to basically create energy from matter. Today we're going to talk about the famous formula you probably learned of before, but I can't even write it properly. The formula E equals mc squared. And we're going to talk about how energy actually comes from mass. We're going to begin with that today. And that's where we're going to go. We're now going to talk about in the 1930s and the 1940s how the United States, there's a famous letter that was written to FDR, the President of the U.S., Franklin Delano Roosevelt, and Einstein wrote it, basically saying, U.S., get your act together. You better build a nuclear bomb before the Nazis do, because if Germany builds a nuclear bomb before you do, then the balance of power in the world is going to be completely upset. I mean, as it was, what the Nazis did in Europe was horrible, right? And hopefully you've learned about some of the social studies implications of this. But from a science point of view, I don't know that we discuss that as much in social studies class. Maybe they do. But we're going to discuss the scientific implications and how science allowed for the advent of the first atomic weapons. And that's where we're going to go today. I've got a few different sub things we're going to do. We're going to start off by talking about basically just how atoms, what the internal structure of atom looks like from a chemistry point of view. We've been discussing the last few days the idea of Rutherford and Bohr and Thomson and Dalton and what they believed matter looked like. Now that scientists had a better understanding of atomic models, their previously incomplete ones were now figured out by protons, neutrons, and electrons. And so now that we know what the internal structure of matter looked like, physicists were then able to understand some more fundamental forces. We're going to discuss today some of the fundamental forces. There's gravity and the electromagnetic force. But we're now going to discuss the last two. First, the strong nuclear force, and then eventually the weak nuclear force. And so maybe I should get on this because there's a lot to cover today. It's kind of a hodgepodge of everything, but it all leads up to a really, really important historical culminating discovery and really the event when the nuclear bombs were created. So let's begin here with maybe my next slide here. I need for you all to be aware of some basic terminology that's mostly chemistry. I need you to be familiar with these terms here. And if you're not, I'm going to give you a mini 3-minute lesson. And so over the next few slides, I'm going to discuss the words atomic number, mass number, isotope, atomic weight, atomic mass, kind of they used interchangeably, atoms, ions, and valence electrons. These are all chemistry terms, but in order to be able to discuss what we're going to discuss, you need to know all of these. Now, I don't want to come across as being a little condescending, but this is, or making light of this, but this is grade 10 science I'm going to do a little review of. I teach this to students in grade 10, so hopefully you're familiar with this, but if not, here's the recap. In chemistry, we talk about the periodic table of elements, right? And we now know that elements are made up of your protons, your neutrons, and electrons. But really, it was physics that allowed scientists to know about these three different things. And your periodic table is literally listed based on how many protons something has. Hydrogen has 1 proton. Helium has 2 protons. Zinc has 30 protons. All of these numbers here are how many protons you have. And we have a name for that. We call it the atomic number. The atomic number right here is how many protons something has. And hopefully, if I haven't given you this already, but hopefully you have a basic periodic table, because you're going to need one in physics. There is some chemistry overlap as we get into the 20th century physics. And so you need to know, first of all, atomic number. Atomic number is how many protons something has. Now, we also give something an atomic symbol, and you may also see an atomic mass on there. This is the average molar mass. And so if you're familiar with chemistry, this is how many grams there are in a mole of substance. That's what this number here stands for. And we don't utilize that. Chemists utilize that, and we can, but we're not going to. So we're not going to use this number right here, 95.94. Although it's listed for us, it's really not the important number. What's more important to us is on an individual level, something like this. We often write out elements in this format, like say C14.6. The bottom number down here is the atomic number. It's how many protons something has. And so carbon has, for sure, 6 protons. But on an individual basis, at a one-at-a-time basis, carbon has to have a certain number of protons, neutrons, and electrons, and they have to be quantized. They have to be in discrete whole number amounts. You can't have 4.5 electrons. You can't have 3.2 neutrons. So this top number up here is known as the mass number, and it tells you in one individual atom how many things are in the nucleus. This is basically your nucleus number. And so if there are 6 protons, then the top number tells you protons plus neutrons. And so I now know that in this particular variety right here, if there are 14 items in the nucleus and 6 of them are protons, there must be 8 neutrons. Now, what's useful for physicists is this tells us how many there is one at a time. And so in one particular carbon atom, there are 8 neutrons, but there could be 9 neutrons or 4 neutrons or 15 neutrons. And if I could go back here, that's what this number right here confuses students on, because this is an average mass when you have 6.02 times 10 to the 23, which is a mole of something. When you have this many atoms or this many particles, this is the average that you're expected to find. But we're not going to work with an average. We're going to talk about either this atom or this atom. We're talking about quantum particles, individual atoms. And so, let's go back to this slide right here. This is known as an isotope. An isotope basically refers to which variety are you using. And if I can go to this slide right here, this talks about the different isotopes we have of carbon. There's carbon 12 and 13 and 14, and they all have 6 protons, because that's what makes it carbon. Carbon has 6 protons. But this one has 6 neutrons, this one has 7 neutrons, this one has 8 neutrons. Now on average, carbon averages 12.01 grams per mole, which means that there's most likely a lot of carbon 12 in the world. There's some carbon 13, there's even some carbon 14, but most of the time it's 12.01. So it's version number 12. Okay. This also over here, this little slide right here talks about how hydrogen works. There's hydrogen 1,1, there's hydrogen 2,1, there's even hydrogen 3,1. Now all hydrogens have 1 proton. But you could have 0 neutron hydrogen, you could have 1 neutron hydrogen, you could have 2 neutron hydrogen. Either way, you always have 1 proton, because by default, hydrogen has 1 proton. And so this means that you can either have hydrogen 1, 2, or 3. Sometimes we write it like this. We write it as hydrogen 1 or hydrogen 2, or carbon 12 or carbon 13. And so these are known as isotopes, and we talk about them one at a time. Now if I can go back to the slide that I've skipped right here, this kind of also relates to how many electrons there are, because protons should equal electrons. If you have an atom, you have no net charge. Okay? An atom is fundamentally neutral. You have 9 protons, you have 9 electrons. But if you've taken any chemistry, even grade 9 or grade 10 chemistry, you should hopefully know that we don't just stay with atoms, we also have ions. And ions are where you gain or lose electrons. And we now understand this better because we believe that the electrons are outside of the nucleus. The nucleus involves all your protons and neutrons, and your electrons are outside of it in those valence shells. We often draw them in orbitals, but we now know that they don't really orbit. They're actually in probabilistic wave functions. We believe they're in like a cloud where they're somewhere in there. We don't know exactly where, but somewhere there's electrons. We often draw them in this Bohr model here where they're in rings. Long story short, though, is that you can either gain or lose electrons. But you can't gain or lose protons, because if you change protons, you change what it is. So this proton number down here, it defines what it is. Mass number, therefore, is the top, and atomic number is the bottom. And what we're going to be discussing today is one of the physics principles known as conservation of nucleons. If you have a certain number of protons, neutrons, and electrons, you have to keep that number. You can't lose them. Okay. Moving forward here, actually, let me go back and just recap here. Hopefully you're then familiar with all of these terminologies I gave there. Okay. Valence electrons are the outermost electrons, and if you gain or lose them, you have ions. atoms means that you're fundamentally neutral. That means you should have equal numbers of protons and electrons, but that doesn't usually happen. Almost everything becomes an ion, unless it's a noble gas, if you know your chemistry. Atomic weight and atomic masses are the averages of 6 kabillion molecules, 6.02 times 10 to the 23. Those are your averages. Isotopes are what you have for a specific one element, and so typically we would give you something like this, N15, 7. And what that would do is it would tell you that it's nitrogen because there's a 7 in the corner, and this has 7 protons, and it would have 8 neutrons. And it probably has 7 electrons because it's an atom. And now, chances are it's going to these electrons, they're going to change. You're going to gain or lose electrons. We're mostly going to focus on the nucleus. And if I could point out something here, electrons are often omitted in physics because they weigh so little. If you look up the masses of protons and neutrons, the masses of protons and neutrons are usually times 10 to the minus 27. But the masses of electrons are times 10 to the minus 31. You would need 1,000 electrons to weigh a proton or a neutron. And so mass-wise, they're tiny. They actually have very little mass compared to protons and neutrons. But charge-wise, protons and electrons actually have the equal amount of charge. It's kind of weird how our universe works out and how that fits. That's what we want to discuss next. So with that little chemistry review done, I want to discuss the beginnings of nuclear physics. And what we want to begin with is the idea of something called an atomic mass unit. Now, we don't use this a lot, okay? This is unlikely to be on your diploma. It was used in a couple of different diploma years, and so I need you to be familiar with it. But rather than measuring things in kilograms, you need to be familiar with the idea of an atomic mass unit, which is often the letter U. And so it's not part of the metric system, but one of the reasons why is that it's kind of crazy to always be measuring things as 1.67 times 10 to the minus 27 kilograms. That's kind of a really, really awkward thing to measure for mass. Remember how when we were talking about energy, we can measure things in joules? But maybe it's better to measure it in an electron volts instead. Maybe that's a better way of measuring because it's so small. Well, that same sort of thing happens when we're talking chemistry and physics at the atomic level. If you have a lot of something, like let's say you're going to use a full mole's worth of carbon, well, then you're going to have 12.01 grams of carbon if you have a mole of it. But if we're talking one particle, like one at a time, or even just a few of them, maybe we need a different unit. And so here's a chart that kind of talks, if you can see this hopefully, it kind of shows all the different ways that we measure masses, but in terms of what's known as atomic mass units. And this right here is the key. We have defined 12 to be what we called carbon-12. So carbon-12, if you recall, carbon-12, let's draw it down here, carbon-12 means that it has 6 protons and 6 protons and 6 neutrons. And that is what has been defined as having 12 atomic mass units. We went with that one as the standard, and everything else gets compared to that. And so if you can look in this chart right here, carbon-12 has 12 particles inside, right? 12 protons, 12 neutrons. We get to kind of ignore the electrons. They don't weigh nearly enough to even notice, right? You need 1,000 electrons plus to even make one proton. So carbon-12 has been given the atomic mass unit of 12, because there's 12 pieces to it, so we went with 12. Right? Carbon is also one of the biggest building blocks in our universe, so that kind of makes sense. Well, it means that then hydrogen weighs 1.008, or what else? Sodium weighs 21.99, and this is all like in comparison. So rather than weighing things out in kilograms or in grams, we can measure them out in atomic mass units. Now, a lot of times students will say, hang on a sec here, this does not match up with my periodic table. I've taken some chemistry, Chris. I know that sodium is 22.99. And I go, yeah, I know. But that's how many grams there is in a mole. And a mole means you have 6.02 times 10 to the 23 particles to average out. We're not talking about averaging a billion particles. We're talking about one. We're talking about literally one particle. And so therefore we can only talk about sodium 22 or 23 or 24. Right? Can you see how we have sodium 22 or 23? We've got to talk about them one particle at a time and see what they weigh comparatively to carbon-12. And that's what basically this says here, is that these U values are based on a neutral carbon-12 And so 1U is 1/12 the mass of carbon-12. So we've weighed out carbon-12. A U is a 12th of it. And so therefore carbon-12 is 12, and everything else is based on that. Long story short, an atomic mass unit is basically 1.66 times 10 to the minus 27. And that's kind of the average of protons and neutrons, right, in a way. Protons and neutrons put together, they more or less weigh this, and it's based on carbon-12, but we haven't talked about something called binding energy yet. And we're going to get to that. First, before we get to binding energy, we have to ask a question here. Hang on a sec here. In the nucleus, you said there's neutrons and protons, right? Rutherford's model of the atom suggested that there's a whole bunch of stuff in the nucleus, and he suggested that electrons kind of orbited around it, and this is a very Rutherford kind of model. But wouldn't all these protons in the nucleus, if I kind of drew them out, there's some protons, there's some neutrons, there's some protons, there's some neutrons. Wouldn't all these protons, wouldn't they want to repel each other? Wouldn't they want to basically bust this nucleus apart? Why don't they? Why doesn't the nucleus basically just split itself apart? Well, it does in certain nuclear reactions. We need to get to that, though. And so physicists have been trying to grapple with the idea of, well, why does a nucleus stay together? And there was a theory. They suggested that maybe gravity keeps them together, because maybe gravity outweighs the electrostatic force, right? Isn't the electrostatic force what is causing proton 1 and proton 2 to basically repel each other? Maybe gravity is able to overcome that and stick them together. Well, we can actually prove that that's not true at all. Now, imagine you have two random protons. Let's say you have proton 1 and proton 2. Right? What we can then say is that however far apart they are, let's say that radius is 1 meter. I know it's not 1 meter, but just for argument's sake, let's say it's 1 meter. Well, electrostatic force would want to push them away, but gravity would want to pull them together. We want to figure out which one is stronger. Well, check out these formulas here, though. The way the formula works for gravity is it would be 6.67 times 10 to the minus 11, and then you'd have to multiply by the mass of 2 protons. So that would be the 1.67 times 10 to the minus 27. I know we're back into kilograms, and I just finished talking about atomic mass units, but let's go with kilograms for now. You'd have to times by another 1.67 times 10 to the minus 27. And when you're done, you'd have to divide by a radius. And so just for argument's sake, let's just say that they're 1 meter apart. Well, now let's compare that to the electrostatic force. The way the electrostatic force works is it's 8.99 times 10 to the 9 times by the charge of a proton. Okay, 1.6 times 10 to the minus 19. Charge of another proton, 1.6 times 10 to the minus 19. And then divide by the distance between them, 1 squared. I don't even need to calculate that. I can guarantee you that gravity is not greater than electrostatic. Because look at these exponents, to the minus 11, to the minus 27, to the minus 27. This is going to be a massively small amount of gravity. Now, I know the electrostatic force isn't that large, but it's definitely bigger than gravity, right? This is to the minus 19, to the minus 19, and to the positive 9. The electrostatic force is not less than gravity, right? I wrote out that, in theory, they suggested, well, what if gravity is greater than electrostatic? But it's not. The electrostatic force is definitely greater than gravity, which once scientists started to grapple with what Rutherford's model meant, they realized that protons would be repelling other protons. And there must be other forces in the universe, ones that we can't measure, ones which we can't see. Now, we can see gravity, and we can see the electromagnetic force. Those are things that we can see the effects of, but there must be other forces keeping a nucleus together, which is where my next slide goes. They theorize that there must be another force that is binding the nucleus together. Otherwise, it would just fly apart. All of these individual little protons would just start bursting apart and breaking. And they do, actually. And we're going to talk about that when we talk about the weak nuclear force, eventually. But the weak nuclear force is what we're going to discuss when we talk about radiation, gamma radiation, and beta and alpha radiation. The strong nuclear force is what we believe is what keeps the nucleus together. And they're theorizing this because, truthfully, we don't really know what's keeping it together. We can't hop on the magic school bus, zoom down to the size of protons and take a look. All we can try to do is test. And so what we do know, though, is that stable nucleuses, stable nuclei, seem to have a strong nuclear force that's greater than the electrostatic force, and it keeps them stuck together. Now, if it's not, we're eventually going to get to this, but radioactive decay takes place, and we can actually have nuclear reactions take place in which energy is then released in the form of gamma radiation or alpha beta particles being given off. We're going to get there. So what we're talking about right now, though, is this new force. They call it the strong nuclear force, for lack of a better name, but scientists really don't know what's going on there. What we do know, though, is that there must be a binding energy keeping all of these things stuck together. In a way, if there's not energy keeping them together, the nucleus would bust apart. And so in order to break a nucleus apart, energy is going to need to be added to break a nucleus apart, because otherwise nucleus would just randomly break. And I like this activation energy diagram for anyone who's taken physics 30, or not physics 30, chemistry 30. This is known as an activation energy diagram that you learn about in Chem 30. And basically the idea is that you have to input some energy to get over the hump. This is called the activation energy amount. And it's kind of good that matter seems to require this, because otherwise all of our matter would just start randomly breaking apart from each other, right? Can you imagine just matter disintegrating? If there wasn't the strong nuclear force keeping protons and protons stuck together in a nucleus, they would bust apart. And so we know we need energy to get them to separate. Hence this picture here. Now, Albert Einstein eventually theorized that he could actually calculate this, and this is where his famous formula comes in, E equals mc squared. And it's known as the mass defect. And probably the best way of me describing the mass defect is to actually do this example first and then come back to talking about it. Okay. So what we've actually done is we've looked up the mass of a zirconium-93 atom. We've actually managed to isolate just zirconium-93. We've weighed it, and we recognize that zirconium-93 weighs 92.90674 atomic mass units. Okay. We're not talking zirconium's molar mass. If you had a periodic table nearby, zirconium's molar mass is 91.22. But we're talking pure zirconium-93s, so 93 atoms the whole way through. This is how much any one of them weighs. Now, what I want to do, though, is I want to calculate the mass of the nucleus particles at a time. So you know how zirconium-93 would be Z, what's zirconium? Zr. And zirconium is atomic number 40, which means that this thing has 40 protons, and if you can do some quick math in your head, it has 53 neutrons. Now, if you go back a few slides in my notes, what you'll discover is that I actually tell you how much on an individual level these things weigh. Now, we often weigh, sorry that it's sideways, but we often weigh protons and neutrons in kilograms. And I have their kilogram masses right here. In general, it's 1.67 times 10 to the minus 27. But if you can kind of see this sideways, if we could measure them one at a time in atomic mass units, which give us a little more precision, they weigh a little bit different. Neutrons are slightly more than protons. Protons are 1.007276. 1.007276. I'm going to write that right here. Protons are 1.007276 atomic mass units. That's a proton. And neutrons are 1.008665. 1.008665. So I want to imagine a scenario here. Oh, I don't want to use that U. That fancy stylized U is for a coefficient of friction. I want to use literally just the letter U. I want to imagine a scenario. Imagine that you went to the store and you needed to go buy apples. And you buy 93 apples in a big bag. So there's 93 subatomic particles. Those are apples in a big bag. And you discover that it weighs 92.9047. You go, okay, cool, that's what they all weigh. But imagine you were to go to the scale and weigh them individually. Well, each individual one, they come in either one of two groups. They're either a proton or a neutron. They weigh a slightly different amount based on protons or neutrons. But you know that you have 40 that weigh this amount and 53 that weigh the slightly more amount. Well, this is where this got really strange for physicists. So if I take 1.007276 and I times by 40, and I add 1.008665 and times by 53, you'll actually discover that it adds up to the number 93.750285. And that is perplexing, because didn't I just add up all of the individual pieces? I just tried to draw the U again there. I want a regular U. Wouldn't all of the individual pieces, should they not equal the final amount? And they didn't. So if I can describe this well enough, again, imagine you go to the store and you go to the scale and you put 40 apples on the scale one at a time. And then you put 53 more apples on the scale one at a time. And you know how much each individual apple weighs because they're consistent. They all weigh the same amount. And then you put them all together and you're like, okay, it should add up to 93.75. And when you're done, it doesn't. It only adds up to 92.90647. Wouldn't that be frustrating and weird? Wouldn't you be like, where did that missing mass go? Well, Einstein theorized that there was a mass defect. And what he theorized is that when you put them all together, there was missing mass. And that missing mass, I like to call it the glue. There is glue holding all of these particles together. And that mass is now missing because it's in the form of energy. And that's where this formula came from. Einstein theorized that mass had been turned into energy, and that energy was then used to keep all of these protons from busting apart. And so imagine that you had a whole bunch of protons, right? And you'd say, okay, well, they're supposed to weigh 93.75. But as soon as you bring them closer and closer and closer together, their mass all of a sudden becomes less. And now all of a sudden they weigh less, apparently. Because weight, or mass, we should really use the proper use, but mass is now gone. And the reason why it's gone is that it's been converted a little bit into energy. And that energy is the glue. If I can use another color here, energy is glue, kind of keeping all of these things kind of stuck together. And so a little bit of mass is now missing. We call that missing mass the mass defect. And so if you wanted to then use Einstein's famous formula, what you do is you subtract the two numbers. So I'm going to take 93.75 and I'm going to subtract what it was weighed when we had pure zirconium 93. We knew this is how much it weighed. When we subtract those two numbers, 52.90647, we get what's known as the mass defect, which is 0.843815 atomic mass units. That's how much missing mass there is. If I times that by 1.66 times 10 to the minus 27, which is how much back on a previous slide an atomic mass unit is worth, if I take that mass and then times by the speed of light squared, so 3.0, I should do times 10 to the 8. This is Einstein's famous formula, 3.00 times 10 to the 8 squared. All of this right here is your mass. This is your speed of light. And that would then be the energy that we believe is tied up in the nucleus, which is keeping all of these protons together. We call it a strong nuclear force. And so I've calculated an energy value here of 1.26 times 10 to the minus 10 joules. Now, that doesn't seem like a whole lot, but that's how much energy is required. Keep in mind, remember when we were calculating forces back here? I know this is force compared to energy, but I mean, we don't need necessarily a lot of energy to overcome this electrostatic force. We just need some energy to overcome this electrostatic force. And so that now explains this strong nuclear force, which again, scientists, we don't really have a great explanation for it. We have some evidence, we have some theories. We can't ride on the magic school bus and go take a look at that force. I can demonstrate to you the effects of gravity. I can demonstrate to you the effects of electricity and magnetism, but all we know about the strong force is that it logically needs to be there, otherwise all these protons would bust apart. So here's what that means then. The mass of the individual particles added up one at a time was supposed to be 93. But when you put them together, it's only 92. Mass was lost. And so if you can kind of imagine that you built a bunch of Lego bricks together. You got a whole bunch of red and yellow and blue Lego bricks. You put them together. Well, as soon as you click them together, apparently they weigh less. And the reason why they weigh less is that in order to have them stick together, you have to lose some mass and transfer it to energy. This is known as mass energy. And it's one of the physics principles on your data sheet. It's the principle of conservation of mass energy. Okay. Let's try one more. Let's try it for magnesium-24. So what we're going to do is we're going to go back to that chart. And we're just going to use that to get us some values. By the way, that chart is not expected for you to memorize on your diploma. They might give you that data. I've got a couple of old diploma questions where they gave you U values for things. But for right now, that's why I put the chart in the notes. So what I need us to go look up is what magnesium-24 weighs. And if you can see right here, magnesium-24 weighs 23,985,042. 23,985,042. 23,985,042. That is how many atomic mass units magnesium weighs together. But it probably weighs more apart. And so if I could weigh it apart, there are 12 protons in magnesium, because magnesium is number 12. And if you have number 24, it means there's 12 neutrons. So I'm going to go back a slide here, and I'm just going to borrow some of this information here. There, I'm going to copy that and paste it right here. So a proton weighs 1.007276 if you're being really specific. A neutron weighs 1.008665. Again, we could work in kilograms, but physicists often like to make their charts in atomic mass units so that you're not always to a small exponential power. So I'm going to times this by 12, times this by 12, because there's 12 of each of them, and add them together. And I'm going to find out how much they weigh if you could have them individually. And so I have them weighing together. Well, no, not together. Sorry, individually. Write that better here. This is individually. If you weighed them individually, they weigh 24.1912, etc. So now that we know that individually all of these particles weighed 24.19 atomic mass units, but together apparently they weigh less, what ended up happening, according to Einstein's formula, E equals mc squared, is that some of the mass has turned itself into energy. Now, I need to make sure you keep these words different. Mass and matter are different things. Mass is a property of matter. Okay? Matter is our stuff. There are still 24 particles there, but apparently those 24 particles became lighter when they came together. There's still 24 of them, but they weigh less. I mean, weigh is not the right word because weight is a function of gravity, but there are still 24 of them. There's less mass there. And that mass got turned into energy, and therefore that energy is what's keeping them all stuck together. So if I want to then do the same thing and calculate the mass defect and the binding energy, I'm going to subtract what they are together. So we've weighed pure uranium-23, or pure uranium-24. Pure uranium-24 actually weighs 23.985042 atomic mass units. So I'm going to subtract those numbers from each other. So I'll take my answer, subtract 23.985042. That leaves me with 0.20625. So that's my missing mass. I'm going to times by 1.66 times 10 to the minus 27. And I'm going to times by the speed of light squared. And that will get me my binding energy. So I'll try this for you guys to follow along. Again, the 1.66 number is on your data sheet. You need to know how to use an atomic mass unit. All these values that you find in this chart right here, they're not on your formula sheet. You may be asked to work with them in this sort of capacity, but that's pretty rare. That's not a common thing to do, but hopefully you've seen now how to solve this. So I'm going to times by 1.66 times 10 to the minus 27, and times by 3 times 10 to the 8th squared. And again, I've got energy of 3.08 etc., times 10 to the minus 11, and that would be joules. And so clearly there is energy found in our nucleus binding it all together. So that's the first part of my lesson. I needed to discuss how scientists were perplexed by a problem, but not for long. If you remember Rutherford's theory about nucleuses, he had a few other problems with it. He was trying to figure out why the electrons didn't spiral into the nucleus. And that's where Bohr came up with energy levels and quantum clouds and probabilistic wave functions for where electrons are. But this also is another problem, is why does the nucleus not bust itself apart? And so we realized that there must be a new force. If I can go back a slide here, there is a strong nuclear force keeping it stuck together. Right? And so now we have three forces we've discussed. You should know about gravity and the electromagnetic force. This is the strong force, which we really can't describe all that well. Well, the next thing I want to discuss is actually the weak nuclear force, which is what happens when a nucleus becomes unstable. Because there are some nucleus which are not able to maintain their strong nuclear force over top of the electrostatic force, right? If you have a strong nuclear force greater than your electrostatic force, here, I'll do it like this. Strong nuclear force greater than electrostatic force means something is stable. It means that all of this is able to stick together quite well. But what happens if it's not? What happens if your electrostatic force becomes greater than your strong nuclear force and this thing wants to start busting apart? Well, then that's what happens under radioactive decay. The nucleus is unstable and a process called transmutation happens. Now, as a bit of a side note, alchemists were working on trying to turn lead into gold. But that's basically what we're talking about right here, is the ability to take a nucleus and break it into pieces. And so therefore it doesn't have to stay the same element anymore. We can actually change elements. And so there are three types of nuclear decays we're going to discuss. The three types are known as alpha, beta, and gamma decay. And so the next few slides are mostly more knowledge and information slides. We will do some more calculations again in a bit, but for right now, we're going to discuss what happens as a logical extension when a nucleus does bust itself into pieces. What happens if the strong nuclear force is not strong enough to maintain keeping a nucleus together? So here's the first one. It's known as alpha decay. Alpha decay occurs when an alpha particle is emitted, and we've discussed alpha particles before. An alpha particle is basically a helium nucleus. It's a 4-2. There's 2 protons, 2 neutrons. 2 protons, 2 neutrons. It has a +2 elementary charge to it. And so what ends up happening is eventually a small little section of this gets booted out. And as it does that, it becomes smaller. But as it becomes smaller, perhaps what ends up happening is it now becomes more stable. And the words we give to this are parent and daughter nucleuses, or nuclei. A parent nucleus is what you start with. A daughter nuclei is what it turns into once you've lost 2 protons and 2 neutrons. Now, alpha particles are actually not that dangerous. When they get emitted, they are large enough that they can't even really go through a sheet of paper. You can deflect them with a magnetic field, by the way, because don't forget, using your hand rules, an alpha particle, which we often draw with this notation, by the way, it's the symbol alpha particle, they have a +2 charge. And so you can deflect them because of the fact that they're charges. Okay? And so that's one type of decay that can occur. Let's do a practice example. There's no math to this, but you are expected to be able to write out basically chemistry equations. Only they're not really chemistry, because in chemistry, if you've ever written out an equation, if I give you, like, say, C4H10 plus O2 forming CO2 plus H2O, in a typical chemistry sort of equation, if you start with carbons and oxygens, you have to end with them. Well, what's going to happen here is we're going to transmutate this, and iridium is going to change what it is. Okay? Iridium-168, the first thing we need to know is, well, what is iridium's bottom number? And if you check out a periodic table, it's number 77, which means this thing has 77 protons. And if I take 168 and minus 77, it means that this particular isotope has 91 neutrons. Okay. That's for this particular isotope. Now, granted, iridium has a molar mass of 192.22, but we're only talking about one particular atom. And so this one particular atom, what's going to happen is it's going to lose an alpha particle. And an alpha particle means it's going to lose 4 total off the top and specifically 2 off the bottom. And so here's how this works. If you're going to lose 2 protons, there used to be 75 protons, but you're losing 2 of these. So if you're losing 2 of these, you're down to 75 protons. And your 91 neutrons, you're losing 2 of those. So now you're down to 89 neutrons. By the way, what I'm doing here is the law of conservation of nucleons, right? I'm losing nucleons. Well, I'm not. I'm kicking out an alpha particle. But when I lose them, I'm down to 75 protons. Well, looking at the periodic table, 75 protons means this thing is going to transmutate into rhenium, because rhenium is number 75. And when I re-add these together, 75 and 89, I have a total number of 164. That's my new mass number. And so this would be using the law of conservation of nucleons, because 168 turned into 4 and 164. Can you see how the math kind of works here? This 168, well, these numbers here still add up to 168. And through law of conservation of charge, 77 protons remains 77 protons. It's just in a slightly different fashion. We've kicked some of them out. In blue, nucleons have been conserved. And in green, charge, protons have been conserved. And so this right here would be an example of an alpha decay of iridium-168. And so it's kind of like a chemistry equation, only what ends up happening is we always have to draw in the top and bottom mass and atomic numbers. Now, in terms of vocabulary, I've already discussed this. It's called the parent is what we start with. The parent is what we start with, and it always turns into a daughter plus a kicked out particle. In this case, it was an alpha particle. And what ends up happening here is that we're always going to lose some mass in the process. Okay? As you read this here, it says the process of alpha decay will cause the mass of the daughter nucleus plus the alpha particle to be less than the mass of the original parent nucleus. And the reason why is that there's extra mass left over, except that mass is turned into energy. And that energy is the 4th type of force. This is radiation that's basically been given off. This is that weak nuclear force, which involves which involves radiation of some kind, energy being given off. And so the parent, when it was stuck together, it had extra energy keeping the nucleus together, right? But it didn't have enough, right? But there was extra energy inside this nucleus, but there wasn't enough to keep it together. And so an alpha particle gets spit off, but in the process of spitting off an alpha particle, energy is released. This is where we're going, people. The idea that when these things occur, a nuclear reaction takes place. That's how nuclear bombs were created, was through the idea of, oh, we can actually make energy. We can actually produce and release energy out of the nucleus. And it really involves all of these different laws. There's laws of conservation of mass. There's laws of conservation of energy. And they got put together into the law of conservation of mass energy, where mass turned into energy. By the way, we can also solve these questions using conservation of momentum principles. I've seen this question often before. Imagine that you have a nucleus that did look like this. And in one direction, the daughter nucleus went. And so the daughter nucleus would be the exact same minus a little bit, because in the other direction went the alpha particle. Can you kind of see how here is the parent? And as the parent spontaneously decays, the daughter could go one way, and the alpha particle could go the other direction. So you can actually do conservation of momentum questions on this too. But for right now, let's just try calculating how much energy we can actually create when uranium undergoes alpha decay. Right? You might recognize uranium as being one of those fissionable materials. That's going to be the topic of next lesson. But uranium is one of those kind of things that can release a lot of energy. So first, let's write out an equation. Let's figure out how uranium-238 is going to alpha decay. First of all, uranium is number 92. Looked it up on your periodic table, and it's number 238. Well, that means that it must have 92 protons. And if I take 238 and minus 92, it has 146 neutrons. Well, if it's going to undergo alpha decay, it's going to drop down to 90 protons, and it's going to drop down to 144 neutrons. And so in doing so, it's going to kick out an alpha particle. And then the daughter nucleus is going to be whoever number 90 is. And looking at the periodic table, number 90 is thorium. And then if I re-add 90 and 144, I get 234, which hopefully makes sense though, because 238 should equal 4 plus 234. And 92 should equal 2 plus 90. Now the question here is, well, how much energy is released? And this is where we're going to need to go back to the charts that I gave earlier, because we're going to need to try to figure out how much mass uranium has. We're going to have to figure out how much mass an alpha particle has, and how much mass thorium has, and we're going to add them together. Like, here's what we're going to do. We're going to find the mass of just uranium-238. Then we're going to find the mass of the alpha particle. We're going to find the mass of thorium-234. And as we put them together, we're then going to try to calculate how much extra mass there is, or how much missing mass there is, because we're going to be missing mass between the two. And the reason why is that all the energy that was in the nucleus trying to keep the 238 together, it wasn't enough. And so as it splits into two pieces, there's going to be an extra amount of energy, hopefully, that we discover. So let's go back and find some values here. Uranium-238. This is going to take a while because I have to write down these values. Uranium-238. I'm going to write them down on a sheet of paper here real quick, actually. So you'll just have to listen to me verbally say this. Uranium-238, U-238, is 238.050788. And then we need thorium. Where's thorium? Oh, here it is. Here's thorium-234, right down below here. Thorium-234 is going to be 234.043601. The last thing we need is the alpha particle. And the alpha particle is actually not listed here because it's right here. It's helium-4. Helium-4 is actually an alpha particle, right? Because helium-4 is going to be 2 protons, 2 neutrons. And so that's going to be 4.002603. So I've written these down on a sheet of paper for myself. I'm now going to go back to the slide we're working on. And by the way, if you're given this on a diploma exam or on a test question, you'll have to be given a chart with this information. So what I'm going to do is I'm going to write out the mass of uranium. I guess I'll write it down below. It was 238.050788. And if I now try to find the mass of the alpha particle, it's a helium nucleus. So helium-4 was 4.002603, and thorium was 234.043601, it looks like. So I'm gonna add these two numbers on my right hand side and see what they add up to. 4.002603 plus 234.043601. And I ended up getting a total mass afterwards of 238.046204. Now let's compare these two numbers here. Which one had more mass? There was more mass before we started. Why was there more mass before we started? Well, basically what's going to happen is there's energy tied up in that nucleus, right? Remember how we discussed beforehand how there's energy in the nucleus? Well, as this nuclear busts into pieces, it's going to lose some of that energy. And so that missing energy is what's going to get released. I'm now going to subtract these two numbers, 238.050788 minus the 238 number that I found. And so the mass defect in this example here is going to cause a loss of 0.004584 atomic mass units. And now I'm going to do the exact same thing I've done before. I'm going to times that by 1.66 times 10 to the minus 27 times by the speed of light squared. And this is how much energy is given off through basically a nuclear reaction. And so I've calculated that there is 6.848 times 10 to the minus 13 joules of energy being given off. And this one's a little different here because the mass of what you have here is actually more than what you have afterwards. And that's because if you know kind of your exo and endothermic graphs, what ends up happening is that there is a loss in energy right here. And so energy is going to be given off. Mass is going to turn itself back into energy. Together, it weighs more, and then apart, they actually end up weighing less. Now, this seems backwards, but that's because now we're talking about splitting a nucleus apart. Back here, when we were doing that exact same sort of thing with equations back here, together and apart were a bit different, because here we were talking about in order to get all of these protons to stick together, in order to get these 12 protons and 12 neutrons to stick together, there must be some energy hidden inside there to make them stick. That's what I proved at first, is that there is energy inside. Now what I'm doing here is I'm saying, well, now that energy, there's a difference from where we started to finish. The amount of energy we had when we started to where we finished is going to be different because our masses are different. There's less mass. And because there's less mass, there's less energy, and we therefore have lost some of that in that format. Now, one last thought before I move on, because I got to keep moving here. This amount right here doesn't seem like a lot of energy, but that is for one atom. For one atom undergoing a nuclear reaction. Well, keep in mind, let's say that we now times it by 6.02 times 10 to the 23, which is a mole. Oops, I did that wrong. Let me retype that in again. If I were to times that by 6.02 times 10 to the 23, which is how many you have in a mole, well, all of a sudden, you'd have 6.1 times 10 to the 11 joules of energy for a mole's worth. Well, now that seems more reasonable. Now there's a lot of energy that can be found in nuclear reactions. So, okay, if you have questions on that, please make sure you ask and let me know. This is a skill you need to possess, but it's going to be based on charts or data that you're given. Basically, it's really easy to do. You find the mass of your beforehand stuff. We call those your reactants, if you know your chemistry. You find your mass of your products. They're not the same. They will always be different. The reason why they're different is that there is a glue holding them together. And when the glue comes apart, it gets re-released in the form of energy. Mass got turned into energy, right? And so as the glue comes apart and changes how they work, basically some of this mass right here gets converted into energy, right? You then just need to take your basic Einstein formula, E equals mc squared, and just be aware that this mass right here is the difference in mass. That mass causes energy to occur. So, okay, now we need to move on. There are other forms of radiation. There's another one known as beta decay. And this is a strange concept. What ends up happening is a neutron converts into a proton and an electron. If you can kind of imagine this, a neutron would be about this big, let's say, right? And inside, it's almost like you can imagine that inside there is a proton and an electron, and they're neutralizing each other together. One thing you might have noticed is that the mass of the neutron, where do I have an example of that? The mass of the neutron was actually a little bit bigger than the mass of the proton. Did you catch that? Protons are 1.007, neutrons are 1.008. Neutrons apparently are slightly bigger. Now, there's not actually an electron and a proton stuck together, but you can almost kind of think of it this way. And so what ends up happening with beta decay is a neutron will actually split itself apart into a positive proton and a negative electron. And the daughter nucleus becomes one proton bigger than before. So what ends up happening in this example, let's use this picture right here, is that cesium was 155. Or sorry, was 55. Cesium is now 55. And what it's going to do is it's going to turn into barium. And barium is 56. If you can't see that, this is now 56. A 55 turned into a 56, and the proton went up by 1. And the reason why is that a neutron changed itself from a neutron into a proton. But in the process, as the neutron turned into a proton, it kicks out an electron. Now, the top number doesn't change at all, because although your neutrons go down by 1, your protons go up by 1. And so therefore your top number of your mass number, it actually doesn't change, but your bottom number does. Now, the electron that goes out, we actually give a special name to it. We call it a beta particle. And it's given the fancy B symbol with a 0 and a -1. The 0, because it really has no mass to it, because electrons weigh basically nothing. But -1, because this bottom number is how much charge it has. And it has a -1 charge. Now, just for your reference, these beta particles, they will also be deflected in a magnetic field because they're negatively charged, but they can be stopped by about 3 millimeters of aluminum. So they're smaller than alpha particles. They're still not necessarily dangerous, but you can stop them with aluminum. So let's try. Oh, do I have an example here? No, I don't have an example. Okay, maybe I'll try to write out this equation here real quick, the one that you see in the example. What we have here is cesium 137, and what it's turned into then is a beta particle, which is a -1 and a 0, and then it's turned into barium 137, but now 56. And if you look at the top numbers, they still all add up to 137. 137 is 0 and 137. But cesium on the bottom, 55, is the same as 56 and a -1. Right? Because in order to go up by a proton, you had to kick out a negative electron. So that's known as beta decay. Now, there's a couple of small little notes here. When scientists were trying to calculate the daughter and parent nucleuses going different directions, the electron was very weird because it was traveling really slowly. When they managed to calculate it, they thought it would travel at high speeds, right? Because you'd think that the electron would go one direction and that the daughter nucleus would go the other direction, right? The parent was in the middle here, so here's the parent nucleus. You'd think that daughter goes one way, electron goes the other way. And they thought it would go high speeds, and it didn't, because there was actually another particle being given off that they eventually discovered called an antineutrino. And we're going to get into this eventually, a little bit more detail. But what you need to know right now is that antineutrinos are known as antimatter. And this is where scientists started to discover that there are actually subatomic particles. There are actually things out there smaller than protons, neutrons, and electrons. For a while, we thought electrons were as small as things could be. But apparently that's not true. There's actually antimatter out there. And the basics of what you need to know about antimatter right now is that we believe that if antimatter ever touched regular matter, it annihilates itself through the formula E = mc². And energy would actually be given off by antimatter and matter touching each other. It's actually what's believed to have happened in the Big Bang, is that there was some antimatter, there was some matter. They came into contact with each other. It exploded in a big furnace of energy, and there was a little bit of extra matter left over than antimatter. So anyways, here's what you need to know. The symbol we give for the antineutrino is V with a line over it, and the line lets you know that it's antimatter. So that's why I wrote this down for unusual beta decay notes, because you just have to kind of go with this for right now. We're going to talk about antimatter in our final lesson a bit more in detail, but for right now, just go with it and just know that there's an antineutrino given off in beta decay. Now, speaking of antimatter, once scientists realized that there was this antimatter out there that kind of has like the opposite somehow, they discovered there's actually something known as a positron. Positrons have been found. They're basically electrons, but rather than being negative, they're positive. So you know how an electron is this really small thing with a negative charge, and it has a mass of 9.11 times 10 to the minus 31. Well, imagine that it had a positive charge, but it still had a mass of 9.11 times 10 to the minus 31. It's like a smaller version of a proton. Or it's like a positive version of an electron, hence the name positron. And so it is basically the doppelganger to electrons, and it's given this symbol here, 0, 1, with the B symbol. We call that beta positive decay. And so it's actually possible to have another type of thing occur, where a proton turns into a neutron, a beta particle, and a neutrino. Not an antineutrino, but a neutrino. And so this thing right here is the antimatter. This beta particle right here, it's the one that almost needs to have the line on top of it, because it's the antimatter version of it. And so that's another crazy sort of decay that we have. And so I've got an example of it. We're going to skip the energy in mega electron volts now, for time's sake. But hopefully you know how we would do it. You'd go look back at the chart and subtract some numbers. But let's just write out the beta decay of thorium. Thorium is number 234. And so thorium, if it undergoes beta decay, thorium's atomic number, I just got to find it on the table here for a second. Thorium is number 90. And so what's going to happen is it has 90 protons, and it has, 234 minus 90. It has 144 neutrons. And what's going to happen is your neutron is going to go down by 1. It's going to become 143 neutrons. But in light of that, your proton is going to go up by 1 and become 91 protons. So what's going to occur is that in order for that to happen, you're going to lose a beta particle, a -1 particle. An electron is given off because you somehow have extra protons, and you can't have that without breaking the law of conservation of charge, which means that this number is now going to go up to 91, making this protactinium, Pa. And it's still going to be 234, though, because if you add these two numbers together, it still adds up to 234. But the top is law of conservation of nucleons. The bottom is law of conservation of charge. If you're all of a sudden going to have +1 proton right here, you're going to need to have +1 electron as well. And so that's the equation for beta decay of thorium-234. While I'm at it, why don't I do beta positive decay? The way beta positive decay works, oh, I should write out one more thing. It also has that antineutrino. Don't forget, it has the antineutrino. We sometimes skip that. But this was really important because it allowed scientists to realize that antimatter exists. Okay. You could also do beta positive decay. The way beta positive decay would work is you'd still start with thorium, but you'd then be creating a beta positive particle, which basically, if you go back to the previous slide I discussed there, what ends up happening is a proton turns into a neutron. So what's going to happen is, remember how before when I wrote this, you had 90 protons and 144 neutrons? A proton is going to go down, and you're going to get 89 protons instead. And your neutrons is going to go up. You're going to get 145 neutrons. And so this is now going to turn into 89. And 89 on the periodic table is actinium, AC. And it would still be 234. And so what ends up happening is a proton turned into a neutron, but it spit off this beta positive particle. As well, it also would spit off just a regular neutrino. And so those would be known as your two possible decays. One is beta positive, one is beta negative. Long story short is that beta negative, so regular old beta decay, but we sometimes call it beta negative. Beta negative means that you actually go up by 1 on the periodic table. Beta positive means you go down by 1 on the periodic table. Okay, you're going to want to ask me some questions about this, I'm sure, but I'm going to move on here because I've still got a little bit left to go through. The last thing I want to talk about in this particular section is gamma decay. And gamma decay is the third type of radiation that's given off. Only it's not a particle. Well, it is, but it's a particle in the way that we know that photons are particles. Whenever a nucleus changes, it needs to adjust itself a little bit, right? Like let's say that this undergoes some decay. There's a beta particle given off. Or, well, yeah, that'll work, right? See how thorium turned into Pa? A beta particle was given off and it upgraded to 91, right? Well, what ends up needs to happen is that this nucleus right here, it needs to like rearrange itself. And as it rearranges itself, it gives off a photon, and it's always in the gamma spectrum of radiation. And so it gives off a gamma wave. Now, it gives it off as a particle, but think of a particle as like a photon, right? And so there's no actual changes in these numbers here. It still stays the same thing. Like here, this is argon 40, staying argon 40. Here, Pa91 stayed at Pa91. But what happened is it gave off another set of radiation. And gamma decay always occurs either after alpha, and this should say, or beta. So either after alpha decay occurs or after beta decay occurs. There's always gamma decay, where the radius rearranges itself and gives off some radiation. And that's a third type. Now, this does not get deflected by a magnetic field. It can't because it's not really a particle in the same way, except it kind of is, it kind of isn't. But it has no charge at least, right? There's no charge. And this stuff will actually be the most dangerous. You need lead in order to stop it, which is why we often use like lead vests for x-rays. So anyways, that's the next section I wanted to discuss, is the idea of all of the decay types that we have. And here's a picture to kind of illustrate them. An alpha decay spits off a 2-2 helium nucleus. Beta decay would spit off an electron. Gamma decay would just spit off a ray of some type. And these are all types of radiation, and they occur when your strong nuclear force is not enough. And basically, the weak nuclear force takes over, and now all of a sudden you end up having this radiation given off. Okay. Here's another picture that kind of illustrates how we can tell the difference between them. If you have a magnetic field, alpha particles would deflect one way because you would use a right-hand rule for an alpha particle. A beta particle would deflect using a left-hand rule. But a gamma ray would actually go through undeflected because it's not charged. It's not a charged particle. So, the last thing we want to talk about with this is that it's actually possible for a decay series to take place, where often multiple things happen. Where, say, thorium turns into radium, but then radium turns into actinium, and actinium turns into francium, and francium turns into astatine. And it takes a while before it finally gets to a stable nucleus. Because remember, the only reason why this occurs is due to instabilities, right? When your electromagnetic force trying to pull a nucleus apart is bigger than your strong nuclear force, then this thing splits apart. But eventually we'll get to the spot where the strong nuclear force, where there is enough strong nuclear energy available to glue it back together. And so often we'll get to something stable. If you look on your periodic table, sometimes you'll see things where there's, let's use one here, AC, actinium, which is number 89. See how there's like a 227? Sometimes there are things that are not stable, where we found them and they exist, but they only exist temporarily. And so there are certain isotopes that are not stable, but they can exist as like part of a series. This would be another one here. Actinium-222 is possible, but it's not going to last long. It's only going to exist for a millisecond before it finally decays into francium. And francium might only exist for a millisecond before it turns into astatine. So like we've actually got, and maybe I'll even have one printed for you, charts that basically show you all of the stable versus non-stable isotopes. There are some isotopes that are stable, and they can stay that way for a while, and there are some that they only last on route to decaying to something else. Okay, last topic. Radioactive decay is very dangerous, but it's also not consistent. Something we need to talk about. And maybe the best way of me describing this is through this picture right here. Imagine that you started with 100 atoms of something. Well, it's eventually going to decay, and it'll turn into 50 atoms and 25 atoms. But it doesn't happen consistently. How do I put this here? Maybe I should go back. I should talk about half-life. For any of you who have done Math 30-1 or 30-2, you should have hopefully heard about half-life. What we've discovered is that this decay, it doesn't happen all at once. It's not like every single particle immediately changes into something else. It kind of happens randomly. And if we look at large numbers of things, like if we look at millions and billions of particles, we can make predictions. But if we were to look at one or two particles, they behave as quantum particles, and they kind of live in a fuzzy state of being decayed or not decayed. This is actually the idea behind Schrodinger's cat. If you've heard the Schrodinger's cat analogy, one of the reasons why Schrodinger's cat is both alive and dead is that particles that are about to transmutate and change into something new, sometimes they have and sometimes they haven't. And we're not really sure what triggers them. We don't know why all of a sudden thorium decides to split off now and it didn't do it earlier. Like, why does it take a long time or a short time? We're not really sure. But what we have discovered is that it follows a pattern known as half-life. And basically half-life is how long it takes for you to have half of what you have left. So now on a big scale, if you had billions and billions and billions of atoms, you'd be able to make a pretty good prediction. But this is where it gets kind of weird, is that say you only had 100 atoms. Well, eventually 100 would cut into 50 and into 25, but then you can't cut 25 in half. This is really important here. You can't cut 25 in half. It's either going to be 12 or 13. And this is back to the mysterious quantum nature of things, where it's like, well, what is it going to be? Is it 12 or 13? We don't really know. We're not really sure whether that extra atom will have decayed or not, right? And so we often need to use what's known as a Geiger counter. And it measures how many decays there are per second, which is known as a becquerel. And a decay per second, if you've ever seen a little Geiger counter, tells you whether or not there's radioactive material nearby. Because this radioactive material may or may not be undergoing a decay. Now, if you have millions of molecules, definitely some of those molecules are decaying. But at any given minute, we don't really know which ones are going to, right? Imagine a nucleus. or just imagine a whole bunch of atoms, not a nucleus. Imagine that there's a whole bunch of atoms of material. This one could decay, but this one might not for a while longer. And then this one could decay, but this one might not for a while. All we know is that in general, we know how long it takes for about half of it to decay. And there is a formula that you may be asked to use. It's based on math 30-1 or 30-2. And hopefully you're familiar with it. It's a pretty straightforward formula. This N over here tells you how much you're going to have left when you're done, usually in terms of grams. This number right here tells you how much you began with. And this number up here in the corner, this N, tells you how many half-lives have occurred. And I'll just show you a couple of examples and then we'll call her a day. So this is a really classic example. Let's say that you have 75 grams of lead-212 and it's going to decay. So let's say it's going to alpha decay. So Pb212. Lead-212, lead is number 82. And so hypothetically, let's say that it's going to alpha decay. It doesn't just do it all at once. It's not like every single particle changes. Some of them decay, some of them don't, and we're not really sure why. This would turn into that would be an 80. Hang on, let me change that. I got distracted. An alpha particle would spit off a 4-2, and you'd be left with an 80 and a 208. I'm just doing some basic math in my head. And 80 apparently would be mercury. So in this hypothetical example, lead is going to decay into mercury. But it's not like every single lead particle is going to decay all at once, right? We just know that they're going to do it randomly, once in a while. But if you have many, many, many particles, we can predict how long it's going to take, right? It would be like, maybe Vegas would be a good example. On any one die roll, Vegas has no idea what's going to happen. But it does know what's going to happen with a law of averages. And that's what we're seeing right here, is if you have 75 grams of lead-212, you have a lot of it. And what we've been able to predict is that lead always gets cut in half every 10.6 hours. I don't know which lead particles are going to turn into mercury, but I know that half of them will be gone in 10.6 hours. I just don't know which ones, hence the fuzzy weirdness of the quantum level. Right? So the way this formula works then is that N equals N0 times 1/2 to the N. And what I'm going to tell you is that I want to have 9.3 grams when I'm done. I'm going to start with 75 grams, and it's going to get cut in half over and over and over again. Now, if you know how to use logarithms, you can actually use logarithms to solve for this exponent up here. But what I usually just tell kids to do, because this should work in most of the cases we're being asked to solve for, is just take 75 and cut it in half. So if I take 75 and divide by 2, I get 37.5. Just going to show a decay sequence. Here's 75. If I cut it in half, I get 37.5. That got cut in half once. If I divide it in half again, I get 18.75. If I divide that in half again, I get 9.375. And so this means that it got cut in half once. It got cut in half a second time. It got cut in half a third time. And so what I really know is that N is 3. I know that I had to cut this in half 3 times. Right? Now you can use logarithms to solve for this exponent, but the way physics 30 is supposed to work is it's always supposed to be a whole number increment. So I basically know that this thing got cut in half 3 times. Right? Now every time it gets cut in half, it takes 10.6 hours. So if I just times that by 10.6, 3 times 10.6, it should take basically 31.8 hours in order to have your 75 grams turn into 9.3. I can't tell you which particles will be the ones to decay, hence the Schrodinger's cat analogy, because we don't really know whether any of those particles are alive or dead, whether they've decayed or whether they have not. But what we can do is we can make a prediction as to how long it will take. So if you're ever given an equation on this, it's fairly straightforward. All you have to do is, if you're solving for a half-life, just figure out how many times it takes to turn a 75 into 93. It took 3 times. I did 75 times by a half 3 times. And so 3 half-lives by 10.6 is how long it takes. Okay, this is approaching 75 minutes, so I'm going to pause and stop the video here, because I believe that's actually it for my lesson here. If you have questions, and I hope you do, please make sure you ask me. Because this was a long lesson involving a lot of different stuff, I made it a YouTube video, but here's hopefully what we've covered. 1, we should have covered some basic chemistry terminology, mostly involving you knowing how these numbers up here work, the 82 and the 212. You need to know how those work. Okay. 2, we discussed strong nuclear force and the idea that we know, according to Rutherford's model, that if there's a nucleus, nucleuses should want to explode apart, and they don't. So one of the reasons why they don't is that there is a binding energy. And we calculated how to find that binding energy using data off of a chart. You may be asked to do this. All you have to do, basically, is just add up what you have before and add up what you have afterwards, and the masses will not be the same. According to Einstein's formula of E equals mc squared, you can then calculate how much energy there is as the glue binding this stuff together. Now, a logical extension of that is the idea that we're showing right here of transmutation, where elements can actually undergo what's known as a decay sequence. And when they undergo decay, they are changing their fundamental nature. They are transmutating from, like, say, mercury into lead or lead into gold. I mean, that's what alchemists wanted, was to make gold. There are no decay series that we're aware of that end at gold, because that would be really cool. Unfortunately, none have been discovered. It usually involves plutonium, uranium, radium, some of those ones that are not stable. And what ends up happening is you either kick out an alpha particle, or you kick out a beta particle, a beta positive particle. Those are the three. You can either have an element that spits out an alpha particle, or a beta particle, or a beta positive particle. And in doing so, the nucleus gets rechanged around a little bit. Energy is given off, which is what's going to be our next topic, the nuclear bomb and how they were able to make nuclear reactions take place. But these are your three types of decay. This is actually the weak nuclear force, because what ends up happening is, as a byproduct, there is always radioactive energy given off as well in the form of gamma radiation. The gamma radiation is the dangerous stuff. The alpha particle and the beta particles can be stopped fairly easily, but the gamma radiation given off by nucleuses rearranging themselves, that's the most dangerous. So, the last thing we talked about is how this doesn't happen all at once, and how there is this formula here. There's a decay formula that we can use to predict how much will be left. I can't tell you which of the particles will have decayed, but I can tell you how many there will be. And that's it. So I think we'll call it quits here, and we will pick this up together in a group lesson in a future day. One of the reasons why I've scheduled it this way is that if we talk about the theory behind this today, we can talk about the advent of the atomic bombs and fission and fusion in a follow-up lesson. So we'll catch up then. So thanks for watching, everybody. We will chat later.